Welcome back to Very Ordinary Differential Equations. In this lecture, we continue talking about substitutions in differential equations, specifically something known as homogeneous equations. So a differential equation is called homogeneous if it can be expressed in the form the derivative of y is some function of y over x. And of course, that's a little odd. We've already been using the term homogeneous for a differential equation of the form y prime plus p of xy equals 0. In other words, the forcing function on the right is just constantly 0. So are we just using the same word for something else? It's not 100% different, but honestly, it really looks that way, and it mostly is. The term homogeneous broadly just means everything looks the same, or everything is the same type. And in math, homogeneous typically means if you rescale the object, it behaves the same or essentially the same under some sort of rescaling. So if a mathematical equation is solved by a bunch of things that look pretty similar, except possibly up to scaling, then the word homogeneous comes into play. So let's take a look at our previous usage of the term homogeneous. Here's what we call a homogeneous differential equation. Y prime plus p of xy is 0. The forcing function is 0. Let's suppose further that y1 is a solution. So if I plug the function y1 in there, it actually works. y1 prime plus p of xy1 is 0. Now I'm going to rescale the function. Pick a constant c and consider the function c times y1. What's the derivative of this new function? Well, the constant factors out of the derivative, and it's just c times y1 prime. Now take this new function y, the rescaled version of our existing solution y1, and see if it also solves the differential equation. Well, cy1 prime plus p of x times cy1, the constant factors out of the derivative, and it also factors out of the other term. And then what do we have? y1 prime plus p of xy1, which we've already assumed is 0, and indeed c times 0 is 0. Overall, if you have any solution y1, then any rescaling of that solution is also a solution. And from the theory of linear algebra, we know that the set of solutions to this beginning differential equation is at most one-dimensional. And what that means is that any two solutions must be linearly dependent, which means that one of them must be a rescaling of the other. So if you find any single solution, all possible solutions are just rescalings of that. So in our previous usage, okay, for the linear first-order differential equation, y prime plus p of xy equals 0, if we find a single solution, then any rescaling is also a solution. But conversely, if we find two solutions, they must be rescalings of each other. So we've expressed this by saying if we find a single solution, then the set of solutions is just all scalar multiples of it. And overall, the set of solutions is just scaled versions of one another. That's what we mean by the term homogeneous. It's the same up to rescaling. The set of solutions is just rescaled versions of one another. Now that's how we've been using the term homogeneous. But from other branches of mathematics, there's the following definition. A function f, and let's just say it's of two variables, is called homogeneous of degree alpha if f of cx and cy is just c to the alpha times f of xy. In other words, if you rescale all of the inputs by the same constant c, there's a very predictable way that the function behaves compared to the original value of f of xy. Rescaling all of the inputs by c, in other words, f of cx comma cy, just rescales the original output f of xy by some power of c. So for example, consider f of xy as x squared minus xy plus y squared. This is homogeneous of degree 2. If I replace x and y with cx and cy respectively, we would get the following. But I can factor a c squared out of every term, and what's left behind is the original f of xy. So replacing x and y with rescaled versions, cx and cy, takes the original output f of xy and scales it by c to the second power. So this is homogeneous of degree 2. Now suppose you have a function f of xy which is homogeneous but specifically of degree 0. In other words, if you rescale the inputs x and y, so f of cx comma cy, what factors out from the function is c to the 0 power, so f of cx cy is actually just equal to f of xy. Then one can see that f actually depends only on the ratio between the two inputs. If we replace x with cx and also replace y with cy, Because the function is homogeneous of degree 0, we've seen that f of cx cy is just f of xy. But if we replace x and y with any values x1, y1 so that the ratio is the same, in other words, y1 over x1 is the same as y over x, well then there must be some constant so that x1 and y1 are simply rescaled versions of x and y. So if we have a function f of xy homogeneous of degree 0, f of cx cy is just the same as f of xy, but also the function really only depends on the ratio y over x. So we can just write that as f of the ratio y over x, if the ratio is all that matters. So any f of this form will also clearly satisfy that f of cy over cx, well the c's cancel out and you just get f of y over x. So any function that can be written as f of y over x is definitely homogeneous of degree 0. So we've matched our new definition. Okay, the first order differential equation is called homogeneous if we have y prime is a function of y over x. In other words, y prime is a function of x and y, which is homogeneous of degree 0 specifically. So let's sum up the two definitions. The earlier definition was to call a linear first order differential equation homogeneous if it has zero forcing function, and it has this property that all solutions must be scalar multiples of one another. The new definition calls a first order differential equation homogeneous if y prime is a function of the ratio y over x, because then the function q is invariant under rescaling of the two inputs x and y. The two definitions are not identical. They have similar motivations. The word homogeneous meaning doesn't really change when you rescale things, but they are, to be totally upfront, just two different definitions being used in the same course, which is unfortunate. Well, how can we solve homogeneous differential equations where we mean our new definition of homogeneous? So suppose I have a differential equation where y prime is some function of the ratio y over x. The right side depends only on one variable, the ratio y over x. So let's do a substitution where u is that variable y over x. Now multiplying both sides by x produces xu equals y. So I'm going to take a derivative and apply the product rule and get u plus xu prime equals y prime. I can solve this for u prime pretty easily. It's y prime minus u divided by x. Now y prime in our original setup is exactly q of u. So y prime gets replaced with q of u. So u prime is q of u minus u over x. This is now a separable differential equation. Okay, I manipulate things around and I get u prime over q of u minus u equals 1 over x. I've got all of my u's on one side with a u prime factored out and all x's on the other. And hopefully you can solve that. So if we started with the homogeneous differential equation, y prime is a function of y over x. Perform the substitution, u is that ratio, and you end up with something separable and hopefully solvable. So let's work through an example. Find the general solution to y prime plus y squared minus x squared is 0. This is very much a nonlinear differential equation. Well, let's see that it's homogeneous first. So what we have to do is get y prime by itself and see that it can be expressed as a function of the ratio y over x. So let's solve for y prime first. Well, if we solve for y prime, we get x squared minus y squared, we divide by xy, and if we split this up into two terms, we get x over y minus y over x. Now we can reimagine that as 1 over y over x minus y over x, which is now more clearly seen to be just a function of that ratio y over x. So if I make that substitution, u equals y over x, we get q of u is 1 over u minus u. Okay, there is our function, 1 over the ratio minus that ratio. So there's my function q of u. I give it a common denominator, we get 1 minus u squared over u. So what we've done so far, we've noticed that this is a homogeneous differential equation. We were able to rewrite y prime as a function of the ratio y over x. We performed the relevant substitution and determined that that function q works out to be q of u is 1 minus u squared over u. Now, the separable form of our differential equation was this formula right here. U prime over Q of U minus U is 1 over X. We just have to take this expression for Q of U, 1 minus U squared over U, plug it in and simplify. It's a little bit of algebra, but it works out to be U times U prime over 1 minus 2U squared equals 1 over X. So we've done a bunch of work and made our substitution to get the separable differential equation U prime over 1 minus 2U squared equals 1 over X. Integrate both sides. The left is this logarithmic term. You can see that you can do a change of variables of just U squared and it works out quite nicely. So we get negative 1/4 times the log of 1 minus 2U squared. On the right we get log X plus a constant. Now I just need to exponentiate both sides to get 1 minus 2U squared equals some constant times X to the minus 4th. Okay, now that constant A is just e to the c from the other side. And we then substitute in U equals Y over X, because remember our original problem was in terms of Y's and X's. And we end up right here. 1 minus 2Y squared over X squared, all in absolute value, is some constant A times X to the minus 4th. Multiplying both sides by X squared gives us X squared minus 2Y squared equals some constant over X squared. Now A is plus or minus e to the c. We had an absolute value here, so this on this side must be positive, but the thing inside the parenthesis could be negative. So 1 minus 2y squared over x squared is plus or minus a times x to the minus 4th. Then multiply by x squared and you get right here. So we have x squared minus 2y squared is some constant over x squared. Okay, we started with a constant, then we exponentiated it to get a positive constant, but then we had a plus or minus that, so we're back to just a general constant, positive or negative. Solving for y squared yields this, and then solving for y introduces a plus or minus. So there is our general solution to the differential equation we started with. This constant can be anything, positive or negative, and we also have a plus or minus here, but altogether, that's all solutions to this differential equation. All right, another example. Let's solve the following initial value problem. Y prime plus 2x minus 3y is 0, and y of 1 is 3. Well, we need to rearrange to get y prime by itself to hopefully recognize a homogeneous form. And we get y prime is 3y minus 2x all divided by y, which simplifies to 3 minus 2 over y over x. We're trying to make every term where the variables appear be the ratio y over x. So we make the change of variables u is y over x. Well then, q of u is just 3 minus 2 over u. Our separable form then becomes u prime over q of u minus u equals 1 over x, which simplifies to u prime over 3u minus 2 minus u squared equals 1 over x. So we've got this separable differential equation here, and now we just need to integrate both sides. Okay, that left side factors. Okay, with a minus sign that we've pulled up into the numerator, u minus 2, u minus 1 in our denominator now. The left is accomplished with partial fraction decomposition. Okay, the u prime factors out and we get negative 2 over u minus 2 plus 1 over u minus 1. And now we can integrate both sides a bit more directly. So we did our partial fraction decomposition and we've made it look like this. We integrate both sides to get negative 2 times the log of u minus 2 plus the log of u minus 1 equals the log of x plus some constant. The initial value problem said that x equals 1. Okay, so in this natural logarithm here, okay, a domain of existence for the solution would either be x positive or x negative, but I can't include x equals 0. Since our initial value had x equals 1, we know we're concerned with positive values of x. Y is also 3 for our initial value, which means that y over x, in other words u, is also positive. It's 3. So that means this term here is positive, this term here is positive, this term here is positive, so all of the absolute values can actually be dropped. Okay. So if I drop the absolute values, we just get this. We can manipulate logarithms to get that this is the log of u minus 1 over u minus 2 squared must be the log of x plus some constant. So we've got that the log of u minus 1 over u minus 2 squared must be log x plus some constant. Now we can exponentiate both sides. As we've done before, e to the c gets replaced with just a. So a is some positive constant. Now I replace my original variables y over x in place of u. So the general solution is given by this nasty expression right here. This does simplify a good amount to just xy minus x squared over y minus 2x squared is a times e to the x. If we now use our initial value information that x is 1 and y is 3, well, we plug them in directly for x and y. Okay, this allows me to solve that a is 2 over e. So we plug that back in. And notice that if a is 2 over e, I get a 2, and dividing by e, I'm just going to reduce this power by 1. So here we have it, the solution to the differential equation we started with the initial values used. As a third example, let's find the general solution for the square root of xy times y prime is x. As before, solve for y prime. It works out quite nicely to just be root x over y. And I'm going to write that as 1 over the square root of y over x. Make our change of variables u equals y over x. Therefore, we get the following separable differential equation, u prime over q of u minus u equals 1 over x. Do a bit of algebra to turn this into root u prime over 1 minus u to the 3/2 is 1 over x. So we've simplified into the following separable differential equation, and now we just need to integrate both sides. The left side is easiest to do by making another substitution, in other words, another change of variables of v equals u to the 3/2. Working through that change of variables will result in 2v prime over 3 times the quantity 1 minus v is equal to 1 over x. That integrates as negative 2/3 times the log of 1 minus v equals log x plus c. Converting back into our variable u gives us this expression in the bottom right. So here's where we are so far. Negative 2/3 times the log of 1 minus u to the 3/2 must be log x plus some constant c. I can combine this into one gigantic logarithmic expression and replace u back with y over x in the following way. And now I just exponentiate both sides. Okay, so x times the quantity 1 minus y over x to the 3/2, all to the 2/3, is some positive constant. And can we solve this for y? So we have this expression, we'd like to solve it for y. So we divide x and raise to the 3/2 power to get that there. Then I just have to move some terms around. And I have y over x to the 3/2 is 1 minus some new constant times x to the minus 3/2. This new constant b is just the original constant a to the 3/2. So here's where we are so far, and our goal to solve for y, we're now a little closer to the end. I just need to raise both sides to the 2/3 and then multiply by x. And we'll end up right here. Y is x times 1 minus some constant times x to the minus 3/2, all to the 2/3. There is a solution to the differential equation, root xy times y prime equals x. So what have we learned? The term homogeneous can be used for multiple different things in mathematics. One meaning, introduced today, is a differential equation where y prime is some function of the ratio y over x. When dealing with a differential equation that is homogeneous in this sense of the word, substituting u equals y over x will create a new differential equation which is separable. U prime over q of u minus u equals 1 over x. And then hopefully you can solve that.